Welcome back in our lesson on Newton's laws of motion. My name is Abdulmajid Talib Khatib, a physics teacher from Susa. Today's lesson will take us through Newton's third law of motion and the principle of conservation of linear momentum, where we will have time in talking about collision. In the previous session, we learned various aspects of Newton's first and second laws. The first law is the law of inertia, and the second is the law of net forces. The third law is the law of action and reaction, which states that to every action there is an equal and opposite reaction. The law emphasizes that force always come in pairs, and it is often called the law of action and reaction. That means that if object A exerts a force on object B, object B must exert an equal and opposite force back on A. Note that the force on A and on B are equal, but this does not mean that their effects are the same, and therefore they cannot cancel each other. Keep in your mind that the third law involves two separate bodies, and the forces occur in pairs only. When any two objects interact with each other, whether it's direct contact or at a distance, they exert forces upon each other. As you sit in your chair, your body acts on the chair with one force, and the chair reacts on your body with yet another force. This is an example of Newton's third law in action. According to Newton's third law, interacting objects experience two forces: action and reaction. The size of the forces acting on one object equals the size of the forces acting on the second object. Additionally, the direction of the force on one object is opposite to the direction of the force on the second object. Consider a man attempting to lift a really heavy weight. If he is able to pull up with a force of 100 Newton, for instance, the weight in turn will pull down with a force of 100 Newton. One among the direct consequences of the Newton's third law of motion is the conservation of momentum. Consider a collision between two objects, object A and object B. When the two objects collide, there is a force on A due to B, FAB, but because of Newton's third law, there is an equal force in the opposite direction on B due to A, FBA, so that FAB equals negative FBA. The forces act between the objects when they are in contact. So the length of time for which the objects are in contact, TAB and TBA, depends on the situation. However, the time must be equal for both balls. Consequently, the impulse experienced by object A and B must be equal in magnitude and opposite in direction. Therefore, FAB times TAB is equal to negative FBA times TBA. Recalling that impulse is equivalent to change in momentum, it follows that the change in momenta of the object is equal but in the opposite directions. This can be equivalently expressed as the sum of the change in momenta being zero. Therefore, the principle of conservation of linear momentum states that if there is no external force acting on a colliding system, total momentum before collision is equal to the total momentum after collision. Conservation of linear momentum expresses the fact that a body or system of bodies in motion retains its total momentum. The product of mass and vector velocity, unless an external force is applied to it. In an isolated system, such as the universe, there are no external forces, so momentum is always conserved. Collisions are particularly interesting to analyze using conservation of momentum. This is because collisions typically happen fast, so the time colliding objects spend interacting is short. A short interaction time means that the impulse due to external forces such as friction during the collision, is very small. There are two types of collisions, which are elastic and inelastic collision. Inelastic collision is the type of collision whereby each body moves with a separate velocity after collision. This is the collision which the object exists in the same state after the collision as before. In this type of collision, there is no loss of kinetic energy, and therefore both energy and momentum are conserved. Example of elastic collisions are two billiard balls bouncing off each other. Elastic collisions only occur when there is no form of energy conversion. On the other hand, inelastic collision is the type of collision whereby all bodies move with the same velocity after collision. This velocity is known as common velocity. In this type of collision, energy is not conserved, only momentum is conserved. Part of the energy is changed to some other form. Consider two bodies of mass m1 and m2 initially moving with velocities u1 and u2. If they collide elastically, and after collision the bodies were moving with v1 and v2 respectively, then by the principle of conservation of linear momentum, we have m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. Consider two bodies of mass m1 and m2 initially moving with velocities u1 and u2. If they collide elastically, and after collision the bodies were moving with v1 and v2 respectively, then by the principle of conservation of linear momentum, we have m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. If the two masses undergo inelastic collision, then after collision they will move with common velocity, that is v1 is equal to v2 equals to v. So that we have m1 u1 plus m2 u2 equals m1 v plus m2 v, which is equal to m1 plus m2 into v. Example 1. A 4 kilogram object is moving to the right at 2 meters per second when it collides elastically head-on with a stationary 6 kilogram object. After the collision, the velocity of the 6 kilogram object is 1.6 meters per second to the right. What is the velocity of the 4 kilogram object after the collision? What is the total kinetic energy before and after collision? We have been given the mass m1 4 kg, its initial velocity u1 is 2 meters per second, m2 6 kg, and its initial speed is 0 meters per second. After collision, the final velocity of 6 kg object v2 is 1.6 meters per second. We are required to find the final velocity of 6 kg. We are required to find the final velocity of the 4 kg object v1 and the total kinetic energy before and after collision. For part A, from the principle of conservation of linear momentum, m1 u1 plus m2 u2 equals m1 v plus m2 v, which is equal to m1 plus m2 into v. We use the formula if m1 u1 plus m2 u2 equals m1 v1 plus m2 v2, and by substitution we have 4 times 2 plus 6 times 0 equals 4 v1 plus 6 times 1.6, so that we have 8 equals 4 v1 plus 9.6, which will give us 4 v1 equals negative 1.6, and therefore v1 equals negative 0.4 meters per second. This means that after colliding 6 kg object, the 4 kg object moved to the left with 0.4 meters per second, as the 6 kg object is moving to the right with 1.6 meters per second. Now for part B, To find kinetic energy before collision, we have to add the kinetic energies of m1 and m2. That is, for m1, its kinetic energy is half m1 u1 squared, which is half times 4 times 2 squared, which gives us 8 joules. And for 6 kilogram object, it is 0, as it was stationary. u1 equals 0. Therefore, the total kinetic energy before collision is 8 joule plus 0 joule, which is 8 joules. After collision, for 4 kilogram object, we have kinetic energy equals half times 4 times 0.4 squared, which is 0.32 joules. And for 6 kilogram object, we have kinetic energy equals half times 6 times 1.6 squared, which gives us 7.68 joules. So the total kinetic energy is 0.32 joules plus 7.68 joules, which is 8 joule. As we can see, the total kinetic energy is the same as before collision. That is, it is conserved as well as momentum. Example 2. Consider the same objects in the example 1 collide, and this time they stick together after the collision. What will be their velocity after collision? Is the total energy conserved? This time we are talking about inelastic collision, so that we have m1 u1 plus m2 u2 equals m1 plus m2 into v. After substitution, we have 4 times 2 plus 6 times 0 equals 4 plus 6 into v, so that 8 equals 10 v, which gives us v equals 8 over 10, so that v is equal to 0.8. Therefore, after collision, their common velocity is 0.8 meter per second to the left. 0.8 meter per second to the right. Total energy before collision, as in the first case, is 8 joule, but after collision, we have half times the total mass, which is 10 times 0.8 squared. It gives us 3.2 joules. Therefore, the total energy after collision is 3.2 joules. So we can say that the total energy is not conserved. Part of it, 7.2 joules, is converted into other forms. That's all I have to tell you about Newton's third law of motion. Remember, it is the law of action and reaction forces. Remember also, one among the consequences of this law is the law of conservation of linear momentum, which is the principle which guides problems concerning collisions. See you on the next session. Thank you for watching.